This is section 2.2a, which is the algebra of functions. And when you see the word algebra, you should be thinking that we are going to be adding, subtracting, multiplying, and dividing functions. Now, when we do this, we have to think about what our allowable domain is, meaning which x's can we actually plug into those functions, and then finding a domain that works with our new function. Okay, so we're going to quickly refresh on how to find the domain, and then we'll look at doing the algebra of some functions and creating a domain that works for those new functions. All right, so if you will recall, when we talk about domain and domain issues in this class, really there's only two types that we're looking for. One is for denominators, right? If we have rational expressions where there's variables in the denominators, our denominators cannot equal 0. Okay, so if there happens to be a denominator, we just set it equal to 0 to figure out what x can't be, right? The other issue that we have is even root restrictions. So meaning if we have a square root, right? If we have an even root, we can't get a negative under it because that creates an imaginary number, right? A complex number, which we can't use to graph. So for even root restrictions, whatever's under our radical has to be greater than or equal to 0. Okay, so it is very important that you know the difference. Okay, that you know denominators can't be zeros, even root has to be greater than or equal to. The biggest mistakes on these problems is getting these two mixed up. Okay, it's the things in the denominator or the bottom of the fraction that can't be 0, the things under a square root which have to stay non-negative. Okay, so let's go ahead and just look at a few examples of trying to determine what our domain would be. Okay, and when we talk about finding the domain of each function, we're going to write our answer in interval notation. Okay, so when we talk about interval notation, we're talking about starting from negative infinity to infinity, and then if we have issues, then we'll take those problem areas out. But originally, we just assume we can plug anything in until we find a restriction. Okay, so let's look at the first one. First thing I look for are my two problems. Do I have denominators, right? Notice here, I don't have any denominators in this, right? So that's not an issue. Second thing I look for is even root radicals. Okay, so notice here, I do have a radical, but it's an odd, right? If you can see that, that's a 3. So this is a cube root, and odd roots we don't have problems on. So that means this function has no restrictions, and no restrictions implies that our domain is all real numbers. So from negative infinity to infinity. Okay, only if we have restrictions do we have to adjust our domain. So let's look at another one. If we look at this next one, I'll ask myself, do I have denominators? Do I have even root radicals? So do I have denominators? Yes. Remember, denominators cannot equal 0. So this means x squared minus 4 cannot equal 0, right? So when I solve this, you could solve it by factoring. I'm going to solve it just by using the square root method. So I'm going to move my 4 to the other side. So I have x squared is equal to positive 4. And then to get rid of the square, I take the square root of both sides. But remember, when you do that, don't forget your plus or minus. So this says that x cannot equal plus or minus 2, right? Because we don't want this to equal 0. All right, so I'm going to go ahead and just write that restriction on a number line because I think we're going to have more than one, right? So on a number line, we have negative 2 and we have positive 2. And right now we're saying it can't equal negative 2, it can't equal positive 2, but it could be anything else on that number line, right? All right, so that was dealing with our denominators. Now we need to look, do we have any even root radicals? And in this case, we do, right? So because we have an even root radical, we know whatever's underneath that radical, our radicand, or in this case our x plus 1, can't be negative. And the way that we say it can't be negative in math is that it has to be greater than or equal to 0. So now I just need to get x by itself. So I subtract 1, which tells me that x is greater than or equal to negative 1. So this is my restriction to ensure that this radical doesn't get negatives under it. So I'm going to go ahead and put that on a number line. Okay, negative 1 is somewhere between negative 2 and positive 2, right? Here's negative 1, and it can equal negative 1, or it can be anything greater than negative 1. So this way, okay? So when I look for the domain of this entire function, I have to find the domain that satisfies all of the problems, okay? Or in other words, I have to take the most restrictive version of this domain. So if I look at what they have in common, what they have in common is from here over, right? So I can't use anything on this side because it doesn't satisfy the second stipulation, right? So looking at what they have in common, it looks like they both include negative 1, right? And then I can go from negative 1, and they're both shaded until I get to 2, right? It can't equal 2, so I have to take the 2 out with a parenthesis. But then on the other side of 2, we don't have any problems. So 2 to infinity. So this is my domain of this function. Does that make sense? We can't stop here and say it can be anything but 2, because then we could end up with negatives under our radical, right? And then we can't just use x is greater than or equal to negative 1, because that would include 2, which we can't include because then we would get a 0. So it's like we're taking the most restrictive combination of those two restrictions to come up with our domain restriction. Okay? Let me look at another one, and then I'll have y'all try one. So on the first one, or on the third one actually, right? We want to go ahead and look, do we have denominators? Yes, we do have denominators. This tells us that the square root of 4 minus x cannot equal 0, okay, because that's in my denominator. Now, it's also an even root radical, and normally with even root radicals, we say that 4 minus x has to be greater than or equal to 0, right? Because we want whatever's underneath our radical to stay non-negative, or in other words, it has to be greater than or equal to 0, right? But because it happens to be in the denominator, we cannot use this equal to bar, right? Because we're saying this whole denominator can't be 0, which means we can't have that equal to bar. So we're going to solve this as 4 minus x is strictly greater than 0. Okay? We only have to do that if our even root radical is in the denominator. If it's in the bottom, we still need it to be positive, but we don't include the 0 because the denominator can never be 0. Okay? If this square root had been up in the top, then I would have left it like this, right? It would be okay for the top to be 0, but because it was in the bottom, I have to take out that equal to bar. And now this is something I can solve. I'm going to move my 4 over by subtracting. So I get negative x is greater than negative 4. And then I just need to divide by negative 1. Now if y'all remember, when you divide an inequality sign, right, not an equation, but when dealing with inequalities, when you divide by a negative, it flips the sign, okay, or reverses the symbol. So what we end up with is x is now less than positive 4. Okay? And again, you don't have to graph it, but if graphing helps you, that means that here we would have a 4. It's less than, so it's not included. So we have an open circle. And then this says that x can be anything smaller than 4, right? Or less than, so it would be going out this direction. So now I want to write interval notation for it, which would be from negative infinity up to 4, with a parenthesis because we're not including the 4 because that would cause the radical to equal a 0 in our denominator. Okay? All right, so there are 3 for y'all to try down here at the bottom of the page. I'm going to give you just a second to go over those, and then whenever you're ready to check yourself, go ahead and unpause the video and we'll go over them and see how you did. All right, so let's see how you did. On number 1, the only issue we have is that we have a denominator. We know that denominators cannot be 0, so we set our denominator so that it's not equal to 0, right, and solve. That means that x cannot be 1/2. Okay, so we put 1/2 on our graph, if that helps you, and it could be anything to the left of 1/2 or anything to the right of 1/2. So in interval notation, our domain would be from negative infinity up to 1/2. We take it out with parentheses, and then anything greater than 1/2 also with parentheses. Okay. When we look at number 2 has two problems. One, it does have a denominator which cannot equal 0. So when we solve that, that means that x cannot equal -1. Okay, so I have that graphed over here on our number line. The only thing it can't be is -1, so we put an open circle there. But we also have an even root radical. Okay, and even root radicals have to be greater than or equal to 0. Right? So I set 7 minus x greater than or equal to 0. I move my 7 over, divide off the negative, which flips my symbol, and I'm left with x is less than or equal to 7. So I went ahead and graphed that on my number line here. From 7, I can go as far as I want to the left. Okay? So these are the two issues we have with this function. So what works for the entire thing is the most restrictive combination of the two. So notice from 7, I can do anything less than 7 as long as I take out -1, which means I can go from -infinity up to -1, take it out with parentheses, and then anything from -1 over to 7. 7 is included on both, so I can use a bracket. Okay? All right, and then the last one, you may have thought we had a restriction because of the cube root, but we actually don't have an issue with this radical because it's a cubed. However, because that radical is in the denominator, we have an issue with a denominator, right? So because it's in the bottom, our cube root can't be 0. And the way to get rid of a cube root is to cube it. So I cube both sides, which basically means that x cannot equal 0. So we can use any number on the entire number line except for 0. So that means we go from -infinity up to 0, and then 0 to infinity. Okay, so now that we know how to find our domain, now we want to go ahead and define the algebra of these functions. Okay, this is how we're going to come up with our new functions. Okay, we can come up with a sum function, which looks like this, f plus g evaluated at x. And what this actually means is that we're just taking f of x and we're adding g of x to it. Okay. Same thing with our difference, f minus g. This just means that we're taking our f of x function and we're subtracting our g of x. Now, if your g of x happens to have more than one term, make sure that you put parentheses around it, right? Because we're subtracting all of g of x, not just the first term. Our product function means we're multiplying. So this is the same thing as saying f of x times g of x. And then our quotient function is f over g of x. So that means we're taking our f of x function and putting it on top of our g of x function, okay, where g of x is not equal to 0. So that's another domain restriction. Now we'd have to worry about where that function equals 0. Okay, so when we start determining our restrictions and how we're going to do these functions, the first thing that we want to do is figure out what are the domain of each individual function. So that way when we combine them, we can find a domain that works for our new functions. Okay, so before we get started, I'm going to go ahead and look at the two functions that were given here and figure out their domains. So when I look at the f function, do I have denominators or even root radicals? Here I don't. So I have no restrictions. No restrictions, which means that my domain is all real numbers. Okay. When I look at my g of x function, I do have a restriction, right? I don't have a denominator, but I have an even root radical. And we know that even root radicals have to stay non-negative, meaning whatever's under our square root here has to be greater than or equal to 0. So if I solve this, I move my 3 to the other side, that tells me that x has to be greater than or equal to -3, right? Or if I write it in interval notation, that'd be from -3 to infinity. So looking at my two domains here, this one can be anything. This one can be -3 or bigger. So the most restrictive combination of the two would be from -3 to infinity. Okay, domain. So any domain that is going to be combining these two functions, we are going to have to restrict the domain so that we're only using values that are between -3 and infinity. because otherwise it's going to be undefined within this g of x one. Okay, so as we come up with these new functions, our sum function, our difference function, our product, and our quotient, we're assuming that this is the domain of each, unless we run into more restrictions. Okay, so let's go ahead, and this is asking us to find f plus g of x, f minus g of x, f times g of x, and f over g of x. So we're finding all 4 new functions, and then we're also going to evaluate the sum function at a couple of values. Okay, so let's go ahead and look at finding these new functions. So I'm going to go ahead and move my paper up here. So when we look for f plus g evaluated at x, this means we're taking our f function and we're adding our g function to it, right? So I'm just going to put in what these two things are. My f function is x plus 1, right? X plus 1. And we're adding our g function to it. Our g function is the square root of x plus 3. So notice there's nothing outside my parentheses that's being done to this x plus 1. So I can go ahead and just drop them, right? So that gives me x plus 1 plus the square root of x plus 3. So I don't have any like terms or anything like that. So this is my new function. Now I need to see, did I acquire any new domain restrictions? So when I look at this, do I have any denominators? Nope. Do I have any even root radicals? Yes, I do. But notice this is the same radical that I already made an accommodation for up here, right? So I've already adjusted my domain accordingly. So my domain is going to be the same. My domain is still going to be from -3 to infinity. Okay? All right, let's look at the difference function. So if I look at f minus g of x, this means I'm taking my f of x function and I'm subtracting my g of x function. So again, I'm going to plug in what those two things are. My f function is x plus 1, and then I'm going to subtract my g function, which is the square root of x plus 3. Now again, there's nothing happening outside my x plus 1 quantity, so I can go ahead and drop those parentheses. And here I can't distribute the negative into a radical, so I'm just going to leave it how it is. So that means my difference function looks like x plus 1 minus the square root of x plus 3. So this is my new difference function. And again, I ask myself, did I acquire any new domain restrictions? Do I have any new denominators? Nope. Do I have any more even root radicals? Well, I do, but it's the one we've already accounted for. So here again, my domain stays the same, -3 to infinity that we originally found. Okay? All right, let's keep going. Let's find our product function now. So we're going to look at f times g of x, which means that we are doing our f of x function times our g of x function. Okay? So I'm going to put those two functions in. We have x plus 1 times the square root of x plus 3. Now normally if this was a polynomial function, we would go ahead and FOIL and distribute and do all that, right? But here we can't because we have a square root. We can't really distribute the square root, values out from under the radical. So here's how I would write it. What I would prefer is just to write it as the quantity x plus 1 times the square root of x plus 3. Okay, I'm totally fine with you leaving it like this. If you want to distribute the square root, you could distribute the square root to each of these values. And you could write this as x times the square root of x plus 3 plus the square root of x plus 3 when you distribute it to the 1. Okay? My math lab should not count it wrong if you go ahead and distribute that out. However, this doesn't do us any favors in terms of simplifying. So I'm going to go ahead and just leave it as the quantity times the radical. Okay, and then I'm going to ask myself, did I acquire any new domain restrictions? Notice I don't have any new denominators, and the only radical I have is the one I've already accounted for. So again, my domain stays the same. So it's going to be -3 to infinity. I know it seems a little redundant to write it after every single one, but in my math lab, when it has you find all these different ones, it'll have you enter the function and then the function's domain. The function and the function's domain. So just trying to mimic that. Okay. All right. Now let's look at our quotient function. So our quotient function, f over g of x, means that we're taking our f of x function and we're dividing it by our g of x function. Okay. So our f of x function is our x plus 1, and our g of x function is the square root of x plus 3. Okay. Luckily for us, they don't make us rationalize the denominator here. So we're going to go ahead and just call that our answer. Okay. And then we need to figure out if our domain has been restricted any further. And it has, right? Because now we have a denominator to worry about. So remember, when we talked about these new functions, when we do the quotient function, it says we can only do it where x is, or where g of x is not equal to 0, meaning our bottom function can't equal 0, right? So if we look at ours right here, that means this cannot equal 0, right? Same thing in here. What would cause this radical to end up being a 0? What would cause it to be 0 is if this x right here was a -3, right? If I plugged a -3 in here, that would make the whole denominator 0. So the only added restriction that we have there is that x cannot equal -3. So from our original domain that said it could be from -3 to infinity, all we have to do is take out the inclusion of that -3. So our domain on this one would be from -3 to infinity, but with a parenthesis to show that we can't actually include that value of -3. Does that make sense? All right, and then they want us to evaluate the function at a couple of given values. They want us to find f plus g of 6 and f plus g of -4. So I'm going to go ahead and go down here. F plus g evaluated at 6. So the first thing I want to check is this 6 in the domain of my sum function? So the sum function was this first one that I found. So here's the function I'm going to be plugging it into as long as it's in this domain. So is 6, right, this is the x that I'm checking, is 6 between -3 and infinity? It is, right, because 6 is bigger than -3. So I can go ahead and plug it in. So what my sum function says is that I'm going to do my input plus 1 plus the square root of my input plus 3. So my input, which here is 6, plus 1 plus the square root of my input, which is 6 plus 3. Right? And now I just need to simplify. So 6 plus 1 gives me 7 plus the square root of 9. 7 and the square root of 9, which is 3, and then 7 plus 3 is 10. So that is the answer when I plug 6 into my sum function. Okay. The second one they wanted me to evaluate again was my sum function, f plus g, evaluated at -4. So now this is the x that I have to make sure is in my domain. So when I look at my f plus g function, again, it's this first one we came up with, is -4 within its domain? It's not, right? Because the domain is from -3 and bigger. -4 is actually smaller than -3. So it's not in the domain. So we're going to say undefined for our answer, because this is not in the domain of f plus g. Okay, and if you were to forget, if you didn't think to check your domain first, if you were to plug in this -4, what's going to happen is you're going to get a negative when you plug in a -4 under here, right? -4 plus 3 would give you the square root of -1, which would give you a complex number. So then you would know, I did it wrong, right? Okay, so that's the general idea. We want to use the given functions to come up with the 4 new functions, okay? Be sure to find the domain first so that you can take the most restrictive combination. That domain should be the domain of every single function you come up with unless you encounter additional restrictions, okay? And then they'll have you plug in a couple of things. So now that we've kind of seen the process, I'm going to take you through a couple examples doing the exact same thing, okay? All right, so starting off, we want to make sure that we find our domain restrictions on each individual function first. So the first one, the f function, notice I don't have any denominators and I don't have any even root radicals. So this one has no restrictions, which means that its domain is all real numbers, negative infinity to infinity. Okay. Then I want to do the same thing with a g function. I look for denominators, which here I have, and even root radicals, which I don't. So here I know the denominator cannot equal 0, right? So I'm going to go ahead and say that x minus 5 can't be 0, which means that x can't be positive 5, right, when I move this 5 to the other side. So that means that my domain, if it can be anything, just not negative 5, would be from negative infinity to 5, and then 5 to infinity. Okay. So I look at all the restrictions for both functions to come up with what I think the domain will be for the combination of f and g as a function. Okay? All right, so looking at my 2 restrictions, the most restrictive combination of the 2 is going to be this one, right? Because this could be anything except 5. So our domain for all of it should be anything but 5, right? So I'm going to go ahead and write from negative infinity to infinity and just take out the 5. So when we do our f plus g, our f minus g, our f times g, and our f over g functions, this should be our domain unless we run into additional issues. Okay, so let's go ahead and see what we can come up with. So f plus g evaluated at x means that we are doing our f function plus our g function. F of x plus g of x. So we're going to go ahead and plug in what those are. Our f function is 2x squared plus our g function, which is 2 over x minus 5. Okay. Now, unfortunately, whenever they give us a function that's rational, they're expecting us to come up with a rational function for our answer, meaning we need a common denominator, right? 2x squared, I can write that over 1. And my least common denominator would need to be what? My least common denominator would have to be x minus 5, right? So this one already has it. This one I would need to multiply on top and bottom by x minus 5. X minus 5 here, x minus 5 here. That way they would have the same denominator, right? So now I have 2x squared times x minus 5 all over x minus 5 plus 2 over x minus 5. And now that they have the same denominator, then I can go ahead and combine the tops, right? And when I combine the tops, I'm going to go ahead and distribute this one. So 2x squared times x is 2x cubed. 2x squared times negative 5 is negative 10x squared, and then I have this plus 2 from the second fraction, all over x minus 5. Okay. Now, normally I would check to see if this can factor. This one does not factor. I could take a 2 out of everything, but it's not going to cancel with anything on bottom, so I'm just going to leave it like this. Okay. So then I have to look for my domain. Okay, the only domain issues I have here, I don't have any even root radicals, I just have a denominator. And here the denominator obviously can't be 5, and our domain has already secured or allotted for that issue. Okay, so here our domain would be the same. Negative infinity to 5, and then 5 to infinity. Okay, because we didn't get any new issues. So let's look at our subtraction function. Our subtraction function is f minus g of x. And this means we're doing f of x function minus our g of x function. So that's going to give me 2x squared minus 2 over x minus 5. And if you notice, these look very similar, right? I'm still going to need a common denominator. It's still going to be x minus 5. And so when I get them both over x minus 5, I should still get this same thing. The only difference here is that I'm subtracting. So I should get the same situation. The only difference is I'll be subtracting the 2 over x minus 5, right? And if I'm subtracting the 2 over x minus 5, then in my answer, this should end up as a subtraction, okay? So instead of write all this out twice, I'm going to go ahead and say we're going to end up with the same thing, other than this 2 should end up negative because I'm subtracting my second term here. Is everybody okay with that? So this gives me 2x cubed minus 10x squared minus 2 all over x minus 5. Okay, and notice, just like our last one, we did not incur any new restrictions, right? The same denominator restriction we had before, so we can go ahead and use the same domain that we came up with originally. Okay, all right, so we found 2 of our functions. Now let's go ahead and figure out our product function and our quotient function. So product function is f times g of x, which means we're taking our f of x function and we're multiplying our g of x function. Okay? So our f of x function is 2x squared, and we're multiplying that times our g function, which is 2 over x minus 5, right? Now, when we're multiplying with fractions, remember we multiply straight across on top, straight across on bottom. And right now, the bottom of my first function, we can just put this over 1, right? So we multiply straight across, which gives us 4x squared all over x minus 5. There's nothing I can do to factor this or simplify, so we just leave it like that. And if you notice, the only domain restriction we have is that original issue in the denominator where x can't be 5. But we already have that covered, so again, our domain is going to stay the same. Negative infinity to 5, 5 to infinity. Okay? All right, we got one more function to come up with, and then we'll do some evaluating. Okay? So our last function to come up with is our quotient function, f over g of x, which means our f function goes on top of our g function. So here my f function is 2x squared, and we're dividing that by my g function, which is 2 over x minus 5. Okay, and I'm going to go ahead and just write this out as a division, right? This fraction bar, when we say something is over something, we can write that as a division. So I'm going to go ahead and say this is the same thing as 2x squared divided by 2 over x minus 5. Right? And since we're dealing with a fraction, I'm going to go ahead and put my 2x squared over 1. Now remember, when we divide fractions, the way that we divide fractions is we multiply by the reciprocal of the second. So this becomes 2x squared over 1 times x minus 5 over 2. Right? So then I can go ahead and multiply straight across. Okay, this quantity needs to stay the same. So I end up with 2x squared times x minus 5 on top, and on bottom 1 times 2 is 2. So there's 2 things I can do. I can reduce by 2, and then I can distribute that x squared inside my quantity. So I end up with x cubed minus 5x squared as my quotient function. Okay. Again, I did not acquire any new issues. I don't have denominators. I don't have even root radicals. So that means that my domain here is going to be the same. Negative infinity to 5, 5 to infinity. Okay? All right. So now that we have all 4 of our functions and the domains for each of them, now we want to see what they wanted us to evaluate. They want us to evaluate f times g of -1 and f minus g of 0. So I'm going to go ahead and just write those down here at the bottom. So they want us to find f times g evaluated at -1. So let's do this one first. F times g. So let's look at that because I need to see, is this x, this x of -1, is it in the domain of f times g? So here's f times g. Here's my f times g function. Is -1 in this domain? My domain says it can be anything smaller than 5 or larger than 5. It just can't be 5. So since -1 is not 5, then I can go ahead and plug it in. Okay? So when I plug it in, my function says to do 4 times my input squared. So 4 times -1 squared over my input minus 5. So -1 minus 5. And then I just simplify. Okay? -1 squared becomes +1. And +1 times 4 is 4. On bottom, -1 minus 5 is -6. And then I can reduce on top and bottom by 2. So this gives me -2/3. Let me just leave it like that. Okay. Second one they wanted me to find is f minus g evaluated at 0. So I want to look at my f minus g function, which was this one showing here at the top of the screen. So here's my f minus g function, and I'm checking to make sure my x, which here is 0, is in my domain. My domain is anything but 5. So since this is not a 5, I should be able to plug in 0. So I'm just going to plug in 0 into this function. This function says to do 2 times my input cubed minus 10 times my input squared minus 2 all over my input minus 5. So everywhere I was saying input, I was inputting 0 for my x, right? So when I plug in 0 everywhere I have an x, notice I'm just left with a -2 on top and a -5 on bottom. Negative over negative becomes positive. So we get 2/5. Okay? Maybe not horrible. All right, let me do one more because I want to do one that both functions have restrictions, just so that you can get practice with one like that. And then I will have y'all try some. Okay? All right, so first thing we want to do is find the domain of each function individually. So f of x, first thing that I notice is that it has a denominator, right? It doesn't have an even root radical, so the denominator is my only problem. But we know that the denominator cannot be 0. So if I solve that, that means that x cannot be +2, right? But it can be anything else. So that means that my domain for the f function would be -infinity to 2, and then 2 to infinity, right? Anything but 2. Now let's look at my g function. My g function has an even root radical, which means that whatever's underneath it, x minus 1 in this case, has to be greater than or equal to 0, right? If I solve this, I would move my 1 to the other side, so that says that x has to be greater than or equal to 1. And the way I would write that is from 1 to infinity. And now I need to take the most restrictive version of these two, okay? If you can think through it in your head, go ahead and do that. If you need to, draw the graph. Okay, so the graph on the first one is that we have 2, right? And it can't be 2, but it could be anything else, right? The second graph says it can be anything bigger than 1. So here's my graph. Here's 1. right? And it can equal 1, or it can be anything bigger than 1. Okay, so I'm looking at what do these graphs have in common. So they have in common from 1 and then going that direction, right? So that means it starts at 1, which is included for both. So I can use a bracket. And then they're both shaded until I get to 2. I have to take out 2 because it doesn't work for the f function, right? But then after 2, notice my shadings go on and on and on. So then we can do anything larger than 2. Okay? So this is going to be my domain for my f and g functions. If I'm adding them, subtracting them, dividing them, this is my starting domain unless I incur more restrictive issues. Okay? All right. So let's go ahead and find our 4 functions. So the first one is f plus g of x, which says that we're taking our f function and we're adding our g function to it. So our f function is 3 over x minus 2, and to that we are going to add our square root of x minus 1. Okay. Now, in order to combine these, we would need a common denominator. So this would be like the square root over 1, right? And our common denominator would be x minus 2, which this one doesn't have. So I would have to multiply on top and bottom by x minus 2, right? So that would give me, now that they both have an x minus 2 denominator, the top of this one was a 3 plus the top of this one. Now remember, with this, I'm not going to make you distribute it, but we do want to write the quantity in front of the square root. Okay, so I'm going to write this as x minus 2 times the square root of x minus 1 all over x minus 2. Okay, so we adjusted so that this one has the same domain, and then once they have the same domain, then we're just adding the tops, right? There's nothing here that I can simplify, so we're going to leave it like that, and then check our domain to see if anything got more restrictive. Notice I have an even root radical and I have a denominator, but they're the exact same ones we already accounted for, right? An x minus 2 in the bottom and a radical of x minus 1. So I have no new issues, so I'm going to go ahead and say that my domain here is going to be 1 included over to 2, and then 2 to infinity. Okay, so no changes. All right, let's look at finding our subtraction function. So f minus g evaluated at x. This one means I'm taking my f of x function and I'm subtracting my g of x function. So notice these two almost look identical. The only difference here is I'm going to have 3 over x minus 2, and then I'm going to be subtracting this one, right? So if I'm subtracting this, I'm still going to have the same process. It's just this bit of it, this is going to be a subtraction instead of an addition, right? So instead of rewrite all this out, I'm just going to say dot, dot, dot. We're going to end up with 3 minus the quantity x minus 2 in front of our square root all over x minus 2. Okay, are you okay with why I did that, how I got that? This is the exact same functions we had above. So going through this same process of getting a common denominator, we're going to end up with the same thing, other than here we had 3 plus that mess. Here we have 3 minus that mess. Okay, so this is my f minus g function, and notice again we have the same restrictions we did originally, so our domain does not need to be adjusted. So it's still going to be 1 included over to 2 not included, and then anything larger than 2. Okay, let's look at our product function. So product function is f times g of x, which means we're taking our f of x function and we're multiplying it by our g of x function. So f of x is 3 over x minus 2, and we're multiplying that by the square root of x minus 1. Okay, again, when we multiply anything that has fractions, we want to make sure we write everything with denominators. So I'm going to put g of x over 1 so that we can multiply straight across. Okay. So this is going to give me 3 times the square root of x minus 1 on top and x minus 2 on bottom. Notice I did not distribute that 3 into the radical because it's outside the radical. I cannot distribute into the x minus 1. Okay. Again, same issues we've had all along. So my domain does not need to be adjusted. So it's going to stay the same. And then we're going to do our last function, which is f over g of x, which says we put our f function on top and our g function on bottom. My f function is 3 over x minus 2, and we're going to divide that by the square root of x minus 1. Now, since I have a fraction, I'm going to go ahead and write both as a fraction. So I'm going to say the square root of x minus 1 over 1. And then I'm going to write this as a division. So we have 3 over x minus 2 divided by the square root of x minus 1 over 1. When we divide, we multiply by the reciprocal. So 3 over x minus 2 times 1 over the square root of x minus 1. And then we can go ahead and just multiply straight across. Now this quantity, I'm going to go ahead and put in parentheses so that I don't forget to put that when I multiply. So on top, I just get a 3. On bottom, I have x minus 1 times the square root of x minus 1. Oh, sorry, x minus 2 times the square root of x minus 1. Okay. Now, did my domain change? Yes, right? Because my radical went from being, notice on all of these, the square root was on the top. And when it's on the top, it's okay for it to equal 0, right? Which the value that causes it to be 0 would be a 1, right? If x is 1, this becomes 0. If x is 1, this becomes 0. If x is 1, this becomes 0. Now it's an issue because if I have a 1 on the bottom, that becomes a 0. I can't have a 0 in the denominator. So right here, I now know that x cannot equal 1. So that's the only adjustment I have to do to my domain is I can no longer use a bracket on the 1. I need to use a parenthesis. Okay. So here my domain is going to be a parenthesis at 1 over to 2 and then 2 to infinity. Okay. All right, so now I have all 4 functions done. So now I want to see about evaluating. I have f plus g evaluated at 2 and f over g evaluated at -4. So I'm going to go ahead and put my f plus g evaluated at 2. So I need to check my x value and make sure that it's okay to plug that in. So this is my sum function. So I go up here to my sum function. This is my sum function. This is my domain. My domain says it cannot equal 2. So this is not in the domain, not in the domain. So that means that my answer would be undefined. Okay. All right, let's look at the second one. The second one is f over g of -4. F over g evaluated at -4. So I want to go ahead and make sure that my x value is within the domain, because otherwise I can't plug it in, right? So I'm looking at my quotient function. So here's my quotient function. Go all the way over. So this is what I'm going to be plugging it into as long as -4 is in the domain. So -4 is not between 1 and 2, nor is it bigger than 2. -4 is like in that direction, right? So this one is also not in the domain. And if it's not in the domain, then it's undefined. Okay? All right, so I've done 3 examples of exactly what I want you to do. Okay? I want you to take the 2 functions that are given, determine each of their domains so that you can take the most restrictive combination of those to figure out what the domain should be for these functions. Okay? That domain should be the domain of all 4 functions unless you come across a more restrictive issue. Okay? Then you'll evaluate 2 of the functions at whatever given values it gives you. Okay, and I believe there's just one like that for y'all to try. Okay, so go ahead and pause the video and try that out, and then we'll go over it. All right, let's see how you did. So the first one has a domain restriction that it has to be greater than or equal to 0, right? Because it's an even root, which means that x has to be greater than or equal to 1. So that would be from 1 to infinity, with 1 being included. And then our second function doesn't have any restriction, so it's all real numbers. So the most restrictive of the two would just be from 1 to infinity. Okay? When we add the two functions, we just add. There's nothing we can combine, so it stays the same, and there's no new restrictions, so our domain is the same. Okay? When we subtract our g function. Now here we do have a little simplifying to do, because when we subtract the entire g function, that's 2 terms. So we need to distribute that subtraction to both terms, which would make them both negative. Okay? No new restrictions, so my domain is still 1 to infinity. On our multiplication or our product function, there's not a lot we can simplify, but I do like to write the quantity in front of the square root. Okay? No new restrictions, so again 1 to infinity. When we do our quotient function, we do have a new restriction, right? Because putting g of x on bottom means that g of x can no longer equal 0. So that means that x can no longer equal -4. Okay? Now, -4 is not within this domain that we've already restricted it down to, right? -4 is like back that direction. So even though this is a restriction, since our current domain is more restricted than that, it doesn't actually affect it. Okay? And then we want to evaluate our quotient function at 5. So we check to make sure 5 is in our domain, and here it is because it's larger than 1. So when I plug in 5 and simplify, I should get 2/9. And then I also want to evaluate our quotient function at -4, which you notice here -4 is not within our domain, so that means it's undefined. We don't even have to work it out. All right, so let's look at the last little bit of this section, which is the easy part of the section. So on all of these ones that we've done so far, we've had to come up with this new function and then evaluate it. Okay, I'm going to show you a way that you can evaluate without coming up with a new function first. Okay, so if they want you to find the new function, then definitely do that. But if they give you something like this, where they give you the two functions and they just say find the functions evaluated at a value, like at 5, and they're not actually asking for f plus g of x, then there's an easier way to do this. Because f plus g evaluated at 5, this just says we want to find f of 5 and we want to find g of 5, and then we could add those two things together. So these are values that we can simplify just by plugging in the 5's into their respective functions, right? So off to the side here, I'm going to find f of 5. So if I plug 5 into my f function says to square my input. So 5 squared is 25, and then subtract 3. So that gives me 22. So f of 5 equals 22. Now I just need to figure out what g of 5 equals. So if I plug 5 into my g function says to do 2 times my input and add 1. So 2 times 5 is 10, plus 1 is 11. So g of 5 equals 11. So now that I know what f of 5 is and I know what g of 5 is, I can add those together to get 33. And that was a lot easier than first having to come up with the f plus g function and then plug 5 into it. Does that make sense? All right, so let's look at another one. The next one is a quotient function, and we've got to be careful with quotient functions, right? Because there could be things that make the denominator 0. So we'll have to pay attention for that. All right, but either way, this still just means we're evaluating f at -1/2 and g at -1/2. So I'm going to do the f of -1/2 first. F of -1/2, f says to square my input and subtract 3. Well, when I square a -1/2, that gives me a positive 1/4, and then I want to subtract 3. 1/4 minus 3 is -2 3/4, right? And then I can turn this back into an improper fraction by doing 4 times 2 plus 3. which would give me negative 11/4, right? 4 times 2 is 8 plus 3 is 11 over 4. So this top piece just becomes negative 11/4 over, now we need to figure out what g of negative 1/2 is. G of negative 1/2, plugged into our g function, we do 2 times our input and add 1. So 2 times negative 1/2 is negative 2/2 plus 1. Negative 2/2 is just negative 1 plus 1 is 0, right? So notice here we're getting a 0 underneath, and when the 0 is underneath, this is undefined. Okay? All right, so there's 2 for y'all to try. Go ahead and pause the video and give those a whirl, and then when you're ready, unpause and we'll go over them. All right, so to find out on number 1 what f minus g evaluated at negative 1 equals, we're going to do f evaluated at negative 1 and g evaluated at negative 1. Figure out what those values are and then subtract them. When you plug negative 1 into our f function, we should get negative 2. When we plug negative 1 into our g function, we should get negative 1. Okay, now remember you're subtracting. So when you subtract a negative, that turns it to positive, which then gives you a negative 1. Okay. Same thing on our product here. We're evaluating at negative 1/2. And so when we plug these in, oh, and I even gave you the same values we did above. So you might have noticed that and not had to work it out again. So when you plug negative 1/2 into your f function, you get negative 11/4. When you plug negative 1/2 into your g function, you should get 0. And then we're doing the product. So product of negative 11/4 and 0 is just 0. All right. All right, got one more thing to show you, and then that will be the end of this section, which is how to do what we just did, but with a graph. Okay, so what we just did is we said if we want to find like f plus g of 0, we could rewrite this as f evaluated at 0 plus g evaluated at 0, right? And then we plug 0 into each function to see what it equaled. We're doing the same thing here. We're still using 0 as our x, right? But we're trying to figure out what it equals. And when we talk about functions and what they equal, that's our y values, okay? So notice here, I was going to see if I had another marker. I don't think I do. Here, I'm going to go over it with red. I'm going to go over this parabola in red just so it's easier to see. You don't have to do this on your paper if you don't want to, but hopefully that helps a little bit. And then we'll go over the curvy one in blue. Whoops. Blue. Blue. See, look how fun math is. We get to color in math, right? Okay. All right. So now that we have what we're looking for, f of 0, this just means our x is 0. So I just go to where our x is 0, which is right here, and I trace it to my f function. So my f function is this blue one, right? And at 0, that blue function is also at 0. Right? And now I just need to see where it is on the g function. So when x is 0, the g function is up at 2. So I take the 0 I got from my f function and the 2 I got from my g function, which means that f plus g evaluated at 0 is just 2. Okay? And then I do the same thing with the other ones. So f minus g evaluated at 1 means we're doing f evaluated at 1 and we're subtracting whatever g evaluated at 1 is, right? So I go to where x is 1, which is right here. I trace it to my f function in blue. At 1, I'm up at positive 1, right? And then I want to subtract my g y value when x is 1. So when x is 1, I trace it to my g curve, which is down here in red, and notice the y value at that point is negative 1. So double negatives make this a positive, so I get 1 plus 1, which means that this one also equals 2. Okay? And we do the same thing with our product. So this is f of negative 3 times g of negative 3. So we're going to go to where x is negative 3, which is right here. When I trace it up to my f curve, my y value at that point is 1. Okay? And then I'm going to be multiplying that by whatever my g value is at negative 3. So at negative 3, notice my g value is down here at negative 1. So positive 1 times negative 1 leaves me with negative 1. Okay? And then our last one is our quotient function. So we're looking at f evaluated at negative 2 over g evaluated at negative 2. So I go to where negative 2 is, which is right here. And notice my f value at that point is right at that point. So that means it has to be 0, right? And then on bottom, g evaluated at negative 2. If I go to where x is negative 2 and trace it to my g curve, it's up here at positive 2. Okay? And 0 divided by 2 is just 0. Okay? All right, so there are 4 for y'all to try at the bottom of the page here. If it helps, go ahead and color in the graphs and figure out what those 4 are evaluated, and then we'll go over them. Okay, so when we look at number 1, we're adding our f and our g values evaluated at 4. F evaluated at negative 4 is up at positive 4. G evaluated at negative 4 is also up at positive 4. And 4 plus 4 gives me 8. On number 2, we're multiplying when we evaluate at x equals negative 2. So at negative 2, our f value is up at 4, and our g value is down at 0. 4 times 0 is 0. Number 3, we're doing the quotient evaluated at x equals 0. So at x equals 0, f is up at 4, and so is g. So 4 over 4 gives me 1. And then my last one is also a quotient at negative 2. And if you notice, we already found the negative 2 values. So f of negative 2 was 4, g of negative 2 was 0. And when we divide those, the zero's underneath, so it's undefined. Okay? All right, that is the end of section, what section is this? 2.2a, I believe. Yes, 2.2a. There's not a worksheet that goes with this one, just a My Math Lab assignment. If you have any questions or need help, please let me know. I'm happy to assist you.